Okay, good morning, dear. Welcome back. This is lecture number 21, and I am today deciding to take a detour or digression to probability statistics and Bayesian formula. I know all of you know about these very important topics, and you have already undergone a full semester course on statistics and probability. But nevertheless, this is so important, and since our couple of future classifiers will exploit the concepts which we will discuss here, there is no harm in recapitulating these important concepts. So as you know, basically statistics is all about collecting sample from the environment, because the environment is large, and we collect sample and analyze the sample, create a model, and from that model we try to predict the environment. So that's all about statistics. And say, for example, census of Indian population, and we are collecting data to know what is the literacy rate and etc. etc. So basically the data has to be random, sampling has to be done randomly, otherwise the model and from the model prediction will be biased. For example, in India there are various states, and all states have their literacy rate varying from say 50 to 90. So we'll have to collect samples from across all the state to get a clear picture, overall picture or global picture about the literacy rate of India. And then suppose through analysis we came to the conclusion that 60% or rather 70% of Indian total population are literate. That means if you come across 10 people, 7 people should be literate, and like that. Okay, so 1,000 people, 700 people, like that. Larger sample, the more the accurate prediction it will be. But this is so far so good. This, let us call it static statistics or frequency based statistics. Okay, where you calculate the event like probability of success, its number of success, the number of possible outcomes, probability of failure, and then number of possible outcomes. And here you express with a numerical index which ranges between 0 and 1, you express the probability. Okay, most events have a probability index strictly between 0 and 1. Okay, and so this is probability of success is equal to this, and probability of failure equal to this, and then p plus q equals to 1. So if equal probable events are there, so probability equals to failure equals to success. Okay, then the probability of getting, say, in tossing a coin, probability of getting a head is 0.5. But you all know that if you toss a coin 10 times, you may not get 5 times head and 5 times tails. But if you toss the coin 1 million times, very likely that half of the million times you will get head and half of the million times you will get tail. So, I mean, you know what I am trying to tell you. Now, this is called so-called static statistics. It has a lot of application. As I told you, globally it can say now somebody from outside India is coming to India, and through your data analysis you have concluded that 70% of Indian population are literate. Okay, so when this is fair enough to get a overall view about India globally, but suppose now a person outside India is coming and entering to a university campus, okay, or an institute campus, triple IT campus. Okay. So that data, is it valid anymore? Means will it be, if you come across 10 people, 7 people will be illiterate and 3 will be illiterate? It's very highly unlikely, right? Here literacy rate is 100%. Okay. So this statistics actually fails to bring the dynamism in statistics locally. When globally you are having some data and you are trying to predict using that data locally, it fails. Okay, and that limitation of frequency-based statistics were understood long before by Thomas Bayes and P.S. Laplace. They are actually independently understood the limitations of static statistics, and then they introduced the concept of conditional probability, where suppose event A and event B is another, there are two events A and B. Suppose A and B are not mutually exclusive. Okay, like in our coin tossing, head and tail were mutually exclusive because both simultaneously cannot occur. Okay, but here suppose they occur conditionally, okay, on the occurrence of the other. Now the probability, then how to calculate the probability, provided an event B has already occurred, then what is the probability of occurring event A? That, according to him, is the number of times A and B can occur divided by the number of times B can occur. This is very intuitively, this formula was developed. Okay. See, this is also called joint probability. Okay, the number of times A and B can occur, or the probability that both A and B will occur, is called the joint probability of A and B. Okay, and mathematically it can be represented by probability of A intersection A and B. Okay, so we can write, this is very intuitive formula, right? A and B, probability of occurring A and B divided by number of times probability of occurring event B. Okay, so that's the probability. Given B, what is the probability of occurring in event A? Okay. Now similarly, the conditional probability of event B occurring, given that event A has already occurred, is equal to this probability. Given A has already occurred, what is the probability that event B will occur, equals to joint probability between the two events B and A divided by A. So if I just form these two equations, if I separate this out, probability of occurring A and B and probability of occurring B and A, so probability of occurring A and B equals to probability of occurring A provided B has already occurred times probability of occurring B, and from here probability of occurring B and A is equals to probability of occurring B given A has already occurred times probability of occurring A, event A. But basically this and this, they are basically same, right? So what we can write, we can just equate these two and then we can write probability of occurring an event A provided the event B has already occurred is equals to probability of occurring B provided A has already occurred times probability of occurring event A divided by the probability of occurring event B. So this is your very famous Bayes rule, as you know. Okay, and this is, I think, from class 12 onwards you guys are learning this formula. It's very, very important formula. Now starting from here, so this is the very fundamental and very basic formula which was introduced by Bayes and Laplace simultaneously, independently, and which is very, very important. See the consequences of this formula. Now, when the event space B is fragmented, now let us suppose what will be the nature of the joint probabilities. That's when precisely what will be the probability of occurring an event A provided B1 has occurred, B2 has occurred, B3 has occurred, B4 has occurred. That means event space B is fragmented. I could be any number. Here it is 1 to 4. It could be 1 to n. Okay. So that can be given by probability of occurring event A provided Bi has occurred times probability of occurring Bi. And slowly we are generalizing so that we can use it for our purpose. Now say instead of event A and B, we are now naming them differently. Suppose we are taking into account both multiple hypotheses. Okay, here in classification problem, these are the multiple classes. Okay, H1, H2 up to Hm, and there are say multiple evidences analogous to our features. Evidence E1, E2 up to say En. Okay. Now, a single evidence E, suppose you are considering a case of single evidence E and multiple hypotheses. So, what will be the probability of multiple hypotheses to be true when it is backed by evidence E? So, again this is same formula taking this step. Okay. Probability that evidence is backed by hypothesis Hi times probability of prior probabilities of this hypothesis Hi divided by k equals to 1 to m, probability of evidence E backed by, so this is the sum of all the probabilities, right, backed by Hk times probability of Hk. Now, multiple evidence and multiple hypotheses, instead of one evidence, now I have multiple hypotheses. I could be 1 to m, and multiple evidences, E could be 1 to n. Then this formula will take the shape of this, that's probability of occurring, probability that given hypothesis Hi, that this hypothesis is supporting so many evidences E1, E2, En, times probability of prior probability of occurring hypothesis Hi divided by this term. You see, it's becoming slowly it is becoming uglier, right? Now, when it was one event, okay, two events A and B, we could directly calculate the conditional probability using this formula. Now, we have event space, evidence space. Event space is large. We have evidences, large number of evidences. Okay, we have large number of hypotheses which could be backed by these evidences, and it turns out that calculating that probability takes this shape. Okay, please try to see here. Okay, this is very ugly. Okay, so this is very ugly formula, which is very difficult for a machine learning engineer to calculate. Okay, in fact, we cannot calculate if it is very large. So then, what you do? We do make some assumptions, and most of the times the assumptions are reasonable assumptions. Okay, so what are the assumptions we are making here? That we are assuming that conditional independence among different evidences. Okay, and if we assume that the evidences are conditionally independent, then the ugly formula can be written in this form, that is, I am writing this multiplication sign. I am introducing the multiplication sign. So this is a probability distribution. This is another probability. This is another probability. This is from probability distributions. I can calculate this. I can calculate this. And since now I have a multiplication sign, how I have? Because I have made some assumption, that conditional independence. Okay, and then I can calculate that. Okay. Formula, which earlier it was impossible to calculate. So now let us try to again write that the probability that multiple evidences is supporting the hypothesis Hi is equals to that probability that all the hypothesis is supporting evidence 1 multiplied by probability of hypothesis supporting evidence 2 multiplied by all this, okay, multiplication term, and divided by the summation of all the probabilities which are now we can calculate. Okay. And incidentally, you also know that since we did this, made this assumption of conditional independence, then the formula is known as naive Bayes formula. Okay, naive Bayes formula. Naive Bayes formula. Okay. So this formula is known as naive Bayes formula, where conditional independence of the evidences are assumed. Okay, because that was our we could not do anything other than that. Okay, we could not calculate without making that assumption when the event space is large. Okay. Now let us try to understand this, digest this formula which already you knew, but I have now written it in a different form with a small example. Suppose we are given this table, okay, where prior probabilities are given. Okay, say we have 3 hypotheses. Okay, and say we are trying to design a classifier which can classify between is a medical diagnosis classifier. Say a patient has come and the classifier is trying to classify from what ailment the patient is suffering from, and patient is backed by some evidences. Okay, and let us see for this example that a patient has come with, say, some rash on the skin, and then she is having also fever, and she is also having some diarrhea. So the classifier need to classify that whether the patient is suffering from maybe measles or chicken pox or maybe allergy. So this is just an example, so that the table can be understood pretty well. Okay, so evidences are rash, temperature and diarrhea. Okay, so and these are the prior probabilities of the hypothesis, right? The hypothesis that patient could be suffering from measles with this probability, from chicken pox with this probability, and from allergy with this probability. Now probability that this hypothesis is backing the evidence, this evidence could be temperature, having temperature like this. Then the hypothesis, all these 3 hypotheses is backing the evidence of diarrhea, say like this, and hypothesis backing the evidence, say rash is like this. So these are the data which somehow, suppose you have got from the model. Okay, you will have to have these, okay, from the data, prior data. Statistics cannot work without data, right? So prior data, from there we have calculated this table. Now suppose I am interested to take a decision now that the evidence E3, what is the probability that my Now my 3 hypotheses is there, and one of them is to be true, right? So I'll have to validate which one is true. Okay, so probability that the hypothesis Hi backed by evidence E3, again this formula you can calculate I equals to 1 to 3 from this table. You can now plug in those values, okay, and just from here you can calculate this formula, and you got a number now 0.34. Okay, now this is the probability of hypothesis 1, say some evidence, this is what I said is Rush is backing hypothesis that it could be allergy, say is this. Same evidence is backing the hypothesis it could be measles, is this, and say is chicken pox with this probability 0.32. Okay. Now at this stage you see we are confused because there is a tie. So of course this is eliminated. So she is not suffering from H3, that means allergy. Okay, so I can now extend the evidence space. Okay, so I am clubbing introducing another evidence. Earlier it was only one evidence, now another evidence E1. Okay, and then I am trying to calculate validate all the hypotheses 1, 2, 3, and here it turns out that earlier, which was likely to be valid, now it has got a low probability, and the hypothesis 2 had got a more probability, and 3 has got less probability. So after bringing in more evidence, this is the hypothesis which is standing. Okay, now let us plug in more evidence. Okay, there are 3 evidences, and then you could see that maybe this will stand and all other will go away. So this is in this way more evidences were plugging in to your hypothesis, and maximum probability were taking, okay, which was standing supported, okay, and you are predicting, your classifier predicting that say hypothesis H2, it could be what I said, it could be measles, right? So she is suffering from measles. So like that you can make a decision. Okay, so now this is the so-called dynamism brought to the static probability. You see, more and more evidence you plug in, when there was only one evidence, situation was something, 2 evidence, situation is something, another evidence, E2, situation will be something, so it will be defined. Okay, so this is the so-called Bayesian statistics. Now say with the prior probability of getting 70% people literate, with that assumption somebody entered in a education institute campus, so he or she can start from there. Okay, that is a priori probability, but now you come across an evidence, that means a people, and you figure out that she is literate, so that probability will go up. Another people you come across, and then it turns out that she is again literate, so the probability will go up a little bit. So more and more evidences, that means in the form of people you come across, and you can just refine your hypothesis, and it may turn out that after interviewing some 100 residents of a university campus, your hypothesis changed. That means you started from a priori probability of 0.7, now it may reach to 0.95, 96, like that. So isn't it a beautiful thing, right? So this is inherent capability of Bayesian statistics to bring the dynamism to the classical statistics and make it relevant for predicting locally. Okay, so with global perception, you come to predict locally, and you become successful if you apply Bayesian formula. Isn't it great? So this is the beauty of Bayesian statistics, and we are going to use this concept for designing our classifiers, which we are going to discuss in the next class. So these are the references. If somebody wants to read books, the wonderful books. So my job is also to introduce you with good materials. Okay, so Pattern Classification by Duda Hart is a classical book and stroke. So this is a book which if you read, you will get almost everything about statistical learning theory. Then another book, very good book, is Artificial Intelligence and Intelligent System Approach by Mikhail Nagnevitsky. Then, of course, these are the books, and then I am following all these materials. This free Coursera machine learning by Andrew NG. Then MIT courseware AI by Patrick Winston, and then StatQuest with Joe Stremer, and there are several numerous other materials. As and when I will come across, I will share it with you. And you can also, if you come across with beautiful materials, you can share it with me. Okay. So with this, I wish you all the best. Stay safe, and bye bye.